Hi everyone, welcome to our video for lesson 4.4. You'll notice that the start of this video looks a little bit different, and that's because there is a handout for the notes today that you're going to fill out as you're watching this lesson. So if you haven't printed out the handout for 4.4 yet, you should stop the video and print out the handout for our notes before you resume the video. All right, so we have learned enough algebra at this point and enough about linear functions that we can start applying linear functions to real world data. And this to me is one of the most exciting parts about algebra because we can start using our math knowledge to analyze real world data and make predictions about events that are going to occur. So today we're going to be looking at statistical data. And we're going to start this with 4.4 and then continue it with lesson 4.5. And we're going to be learning how we can use data sets to model behavior. So we're going to look at a few different questions today. Things like, how is a vehicle's fuel efficiency affected by the weight of the vehicle? Or are average IQ and a person's height related to one another? Or, my personal favorite, does time spent studying affect your Algebra 1 exam test scores? And to look at all of these things, we can basically, we can create linear models using linear equations from data sets to answer all three of these questions in very precise and accurate and scientific ways. So we're going to start looking at that together. And before we can do that, we need to build up some vocabulary together first. And the first thing we're going to look at is something called correlation. And correlation between two independent and dependent variables describes the relationship between those variables. And specifically, we're going to be looking at data sets that have linear correlation, because linear correlation means that the relationship between the variables can be approximated by a straight line, which we can write an equation for. The correlation between two variables is essentially a mathematical tool that helps us relate real-world data to one another. And correlation basically has three options. Correlation can be positive, and if correlation is positive, it means that the data have an upward trend from left to right. So in other words, an example of positively correlated data might be if you collected a bunch of data on a data set and it kind of looked like this. It has an upward trend from left to right. Similarly, negatively correlated data shows that you have a downward trend from left to right. So again, you might collect a bunch of data in a data set, and maybe the result kind of looks like that. And you can see that if you drew an imaginary line through that data set, it would have a negative downward slope, meaning it has negative correlation. Finally, you might have no correlation whatsoever. And that just means that the data aren't related to each other in a linear manner. So maybe I just collect a bunch of data and it kind of looks like that. And I'm like, well, I really don't know. I mean, I could draw a vertical line through that data set to split it, a horizontal line, diagonal line. There's no obvious relationship to that data. So that means it does not have any type of linear correlation. Now, the reason linear correlation is really important is because if data have linear correlation, then we can draw a line of best fit that approximates the data set. And this is really important, so I want you to underline this. The line of best fit is not a line that goes through all the data points. We're not doing connect the dots here. Instead, a line of best fit should cut through the data such that the data are evenly distributed above and below the line of best fit. So for example, if we want to label the independent and dependent variables on a graph, and then describe the correlation and draw a line of best fit, we can do that. So for example, the first data set compares the weight of a vehicle to the miles per gallon, the fuel efficiency. So for this problem, the weight of the vehicle, this would be our independent variable, and the miles per gallon would be our dependent variable because the miles depends on the weight. The correlation here is clearly negative. It's going down. And if we want to draw a line of best fit through this, our goal is to draw a straight line that accurately bisects the data. In other words, it cuts it in half so that half the data is above the line and half the data is below the line. And I'll do the best I can here. Yours will probably be more accurate than mine will be, especially because you should be using a ruler for this. But my line of best fit line might look something like this, where half the data points approximately are above the line, half the data points approximately are below the line. Now the next data set here compares IQ score and height. And as you can see here, it's pretty clear that there's actually no correlation between IQ score and height. Now our IQ score obviously would be our independent variable, and our height would be our dependent variable in this case. However, because there's no real correlation here, we can't really say that height depends on IQ score or IQ score depends on height. So there is no line of best fit for this problem. Now the last problem would be time spent studying on a test and the data points associated with that for grades on an algebra test. So our time spent studying would be our independent variable, and our grade depends on the time we spend studying, so that would be our dependent variable. And in this case, we have a positive correlation. So in other words, we could draw a line through this data set that bisects the data, and that line of best fit is essentially the line that most accurately represents that data set. And we're going to talk a lot more about lines of best fit in 4.5 as well. One other piece of new vocabulary that we need to talk about as we're trying to fit real-world data to algebraic models is something called a correlation coefficient. Because we can describe the correlation within a data set, but we also want to describe exactly how precisely the data models a linear correlation. So we have this correlation coefficient. It's a statistic that we can calculate. It's denoted by the letter R, and it gives a mathematical description of how closely the data actually fall to the line of best fit. So in other words, are the data very tightly packed around the line of best fit, or are they very spread out away from the line of best fit? So if the data are positively correlated, the correlation coefficient is going to fall somewhere between 0 and 1. The closer the correlation coefficient is to 1, the closer the data fall to the line of best fit. So you might have a correlation coefficient that's like 0.98, which means that the data are a really good match for the line of best fit. Or you might have a correlation coefficient that's like 0.2, which means that really the data are pretty spread out. They don't fit the line of best fit that well. Now, if the data are negatively correlated, then the correlation coefficient is going to be between -1 and 0. This time, the closer it is to -1, the closer the data fall to the line of best fit. So in other words, the larger the absolute value of the correlation coefficient, the more accurate your line of best fit is. If the correlation coefficient is 0, then the data aren't correlated at all in a linear fashion. So then we have no correlation for the data. So we're going to talk a little bit about how you calculate the correlation coefficient in 4.5. Today we're just going to analyze it a little bit. So for example, imagine that you're given this scatter plot below, and we want to pick which of the 4 correlation coefficients best describes the correlation between the 2 variables. I'd like you to try this one on your own first, and then so pause the video and then resume the video when you think you have the answer. All right, so for this problem, we can rule out a couple of these right away. It cannot be R equals 1, because that's perfect correlation. It means that the data points would all fall exactly on a line of best fit. If I draw a line of best fit through this data set, it's pretty clear that that's not the case. Similarly, we can rule out number 4 because it has a negative correlation coefficient, but the data here are clearly positively correlated. So that brings us to 1 or 2. And for this problem, you actually don't have any scale, so you could justify either answer. I would probably pick number 1 as more likely because the data are pretty well packed around that line of best fit. But because there's no scale, I could also accept a justification for 0.28 as well. But the main things here to note are that the correlation coefficient has to be positive because it's got an upward slope. And the other thing I would note is that the data points are close to the line of best fit. So those are the 2 things I'd be looking at if I was doing this problem. So let's look at another. Which of the following scatter plots have a correlation coefficient closest to -1? So again, I want you to try this and then resume the video when you think you've got the answer. All right, so we can rule out, again, 2 of these right away. This one has a positive correlation coefficient, so it definitely can't be number 1. Number 3 has essentially no correlation coefficient. They're pretty randomly dispersed. So it has to be 1 or 2. And between these 2, the data points in number 4 are more closely packed together. So number 4 would have the correlation coefficient closest to -1. All right, our last activity for a correlation coefficient here, I have a matching activity where we've got 6 graphs of data, 6 correlation coefficients, and 6 verbal descriptions of those correlation coefficients. I would like you to see if you can connect each graph to a correlation coefficient as well as a explanation about it. So for example, for part A, I'd look at that one and I'd say it's negative, and they're pretty spread out. So if I look at these, that would tell me that it probably goes to R equals -0.56 because it's the smaller of the 2 negative correlation coefficients. And if I look at the words over here, between moderate negative and weak negative, I would say that this would be weak negative. So see if you can connect the rest of these and then resume the video as soon as you're ready. All right, for part B, I can see that it's positive, and I can see that it is well correlated, although perhaps not perfectly correlated. So I would probably connect that to the bottom one, and then connect that to strong positive as well. Part C is perfectly positive. So I would connect that to R equals 1 and perfect positive. D has no correlation at all, so that would connect to R equals 0 and no correlation. And then E has a negative and good correlation, so I would connect that to R equals -0.82 and moderate negative. And then finally, I've got this one that's positive but not very, it's fairly poorly scattered. So I would connect that to 0.35 and I would connect that to weak positive. All right, so the last thing we're going to do here is we're going to talk about how you actually estimate the equation of a line of best fit. And there's 3 steps to do this, which I would like you to write down on your note sheet. So when we want to estimate a line of best fit, the first thing that we're going to do is we're going to draw a line through the scatter plot. And as a reminder, it should not evenly, or it should evenly divide the data points, but does not need to go through all of them. And in fact, it should not go through all of them. Next, to estimate a line of best fit, we're going to pick any 2 points on the line we drew in. And then finally, we're going to determine equation for the line of best fit from those 2 points. And if you think about it, we probably want to use point slope form to do that because we have 2 points. However, if we want to make predictions, we're probably going to want our form ultimately to end up in slope-intercept form. Because if we're in slope-intercept form, that's the easiest way to make predictions about the future because y is alone. And so if we can pick any x value that we want to and plug it in and immediately come up with our y value. So in all likelihood, we're going to be going from point slope form to slope intercept form. So if you need to, pause the video to finish writing down these 3 steps, and then we're going to do one final example together. All right, so this is real data, real life data. The Centers for Disease Control, the CDC, has been collecting data on the percent of children from age 12 to 19 that were considered obese between the years 1971 and 2007. And I included the data in the table on the right. So our goal here is to create a graph of this data to describe the correlation of the data set and pick the most appropriate correlation coefficient. And then we also want to write an equation that models this data set. And so when we do this, I already plotted the data for you, just to save a little bit of time. So the correlation of this data set is pretty clearly positive. And if we wanted to pick the most accurate correlation coefficient, we can obviously rule out the negative ones as well as 0. And in this case, you could pick either 0.25 or 0.88, depending on your feeling about how well correlated the data is. I would say that this data is pretty well correlated. It's got a pretty tight distribution to it. So I'd probably lean towards 0.88, but you could go either way. And we're going to learn how to actually calculate R in 4.5, so then you'll have a more accurate description of it. So finally, though, so we want to draw in our line of best fit. And we want to do the best we can to make it a straight, accurate line that cuts through all of the data. And so as I'm going in and drawing this, I want to do the very best I can to make it as accurate as I possibly can. So I'm going to try to draw in a really straight line that kind of slices through the data. So about half the data points are below the line, and about half the data points are above the line. So then the next thing we want to do is we want to write an equation for this data set. And one thing to make this a little bit easier, you probably remember from a few lessons back in when we talked about when we have data that's based on years, it's often easiest to reset the time from 0 on the y-axis. So in other words, instead of using 1970, 1980, and so on, I'm just going to reset this data to be 0, 10, 20, 30, 40. In other words, years from 1970, just to make it a little bit easier. So now we're going to go through our 3 steps. So we did draw a line through the scatter plot. Step 2 said pick 2 points on the line of best fit, not 2 data points. So I'm going to look at my line of best fit, and I'm going to try to pick 2 points, and ideally 2 points that are on grid lines, or so that we know exactly what those points are. So for example, if I look on my line of best fit here, I pretty clearly have a point right there. And I can kind of see that I also have another point right here as well. You can pick any 2 points on your line of best fit. It really doesn't make any difference. This is just an estimate anyways. So you're going to pick any 2 points. Ideally, further away tends to give you a more accurate estimate. So I've got 2 points selected here. My first point is 10, 9. And then my second point seems to be 20, 13. Now your 2 points might differ from my 2 points because you might pick 2 other points on the line. Your line may not even look exactly like mine. It's really just an estimate. So let's see if we can calculate the equation for this line of best fit. We've got 2 points, which means we can find the slope. So m equals 13 minus 9 over 20 minus 10, which is 4 over 10, or in other words, 2/5, which is 0.4, right? Now yours might be different than mine, right? But it should be somewhere reasonably close to that. So then we can write an equation in point slope form, and we can pick either point. I'll choose the 10, 9 point. So y minus 9 equals 2/5 times x minus 10. And then finally, we probably do want to convert this to slope-intercept form. We'll talk about y a little bit more in 4.5, but it's easier to make predictions if we're in slope-intercept form. So I'm going to distribute the 2/5. Y minus 9 equals 2/5 x minus, so 10 divided by 5 is 2, times 2 is 4, so 2/5 times 4. And then I'm going to add 9 to both sides. And I'm going to come up with an equation of y equals 2/5 x plus 5. So this would be the equation for the line of best fit that best predicts this data set, or best models this data set. Now yours might be a little bit different. Say you might end up with 3/7 x plus 5.5 or something like that. And that's fine, because we're just making a prediction here, an estimate, using 2 data points. Your 2 points might be different than mine. Your line might also be a little bit different than mine, as long as it's reasonably similar. Now the really cool thing about this is we can use this to predict the percentage of obese children in future years. So for example, we could use this to predict the percentage of childhood obesity in 2020, because 2020 is 50 years from 1970. So we could plug in 50 for x, and we would come up with 2/5 times 50, which is 50 divided by 5 is 10, times 2 is 20, 20 plus 5. If this, using this model, we would come up with a 2020 prediction of 25% childhood obesity in 2020. And so you can see, like, the idea here is you can use pre-existing data, a line of best fit, and an equation for the line of best fit to predict future results, which is pretty cool and extremely powerful. So that brings us to the end of our video on lesson 4.4. Try the homework. Please be careful. Look at the assignment sheet for the specific instructions, and let me know if you have any questions. And make sure that you use graph paper as well, because you will be graphing.